Good afternoon. Today I'm going to talk a little bit about some applications of extremums. So, one of the most important parts of working with applications of uh, extreme values is looking at word problems and then kind of like deciding the best approach needed for them. So, the following is a classical problem dealing with Postal Service regulations. So let's just read this. The U.S. Postal Service stipulates that any boxes sent through the mail must have a length plus the girth totaling no more than 108 inches. Find the dimensions of the box with maximum volume that can be sent through the U.S. mail, assuming that the width and the height of the boxes are equal. Now, essentially, one thing that we should realize is what was the given information and what are we trying to find. So, for instance, we know that the wraparound of the box must be no more than 108 inches. So in that case, we can kind of like just kind of select our given information. So, okay, so we have that there's 108 inches that it cannot be no more than. And we see that we're trying to maximize the volume. So in that sense, we can actually go ahead and use those two bits of information because essentially we have um, that the objective is that we maximize the volume, and the constraint is that the girth plus the length would be no more than 108 inches. So with that, that's going to tell us that if we were to suppose that the height and the width is equal, then in that case, we can just say that that's just going to be x. And let's write that this is going to be x and that the length is going to be y. So what that tells us is that the wraparound plus the length would have to be 4x plus y equals to 108. Now, the reason that we say 108 is just so that we maximize the volume as much as possible. So, in that case, the other bit of information that we were given is that we're trying to maximize the volume. Now, volume is essentially length times width times height. So, in our case, we can just say that we're just going to multiply x times y, which that should give us the following equation, x squared times y. Now, in this case, notice that we can express the volume with respect to the x variable, but to do that, we must solve for y in actuality first. So let's go ahead and just solve for y. So we have that y equals to, manipulating this equation, we have that that's going to be 108 minus 4x. Now, what we would have to do next is we would go ahead and substitute the y variable into our volume equation. So in that case, we have that the volume with respect to just a single variable now is going to be v of x equals to, okay, so we're going to write x squared multiplied by 108 minus 4x, and then we just close it. Now, one thing to note is that essentially we have our equation, but notice that we have that the domain must be actually specified for this one. So if we go ahead and we were to set each of these two factors to 0, we would basically figure out that the variable x must be in the open interval from 0 to 27. Now, what that means is that basically if we were to say, for example, let the x variable equal to 0, then the volume would actually be equal to 0, and we don't want that. The 27 just tells us that, well, 27 times 4 is should be 108, so that also gives you a volume of 0, which that doesn't work out. Now, most of the time, in actuality, you might find that a textbook will actually include brackets. Um, Really, okay, yeah, maybe we can go ahead and just make this bracket. And the only reason that they make it a bracket is so that you can guarantee for sure that there's going to be an absolute extremum in this case. So, in either sense, we know that, yeah, if we choose the endpoint, that it's just going to be 0. So definitely it's not at these endpoints. Okay. Now, my next step is that what I'm going to want to do is I'm going to want to optimize the volume equation with respect to x. So that way we'll know what the proper dimensions of this equation happens to be. So go ahead and take the volume equation, and let's go ahead and distribute the x squared, so that way we have that this is equal to 108x squared minus 4x cubed. Okay, so this is still our volume equation. We haven't really done anything with it, but now we can go ahead and find the first derivative. Now, note that the first derivative is just taken by using the power rule, which in this case would give us that 216x minus 12x squared. And we did that just by using the power rule, okay? Now, if we go ahead and set this equation equal to 0, we can actually find the critical points, which means that essentially we can go ahead and set this equal to 0, and then go ahead and figure out like where we might have a maximum if it exists, which, I mean, if it didn't, then that would be that like we kind of wasted our time essentially. But you know, sometimes that may happen, but not when you're learning it, to be honest. So what we can do now is let's go ahead and actually go ahead and rewrite the equation before we even start. That way, for simplicity, we can say that, okay, we know where the equation will equal to 0 because I've already simplified it as much as possible. So for instance, if I factor out a 12x from the two terms, basically I'm going to find that this is going to give me 18 minus x. Now, rewriting it like this, I can basically see that the critical points for this equation are such that x has to equal to 0 and that x has to equal to 18. However, I do have that essentially we can't have that one of the endpoints is our critical point due to the fact that, well, at 0 it's just going to be 0, so we can't do anything with this. But we can check out 18. Now, we did show that we can actually go ahead and, find whether or not this critical point is going to be a maximum or not. So in this case, it actually can be shown by either doing an interval line test or by doing a second derivative test. So let's go ahead and just do a interval line test of where we set up our interval line as so. And note that basically, we have that one of the bounds is 0 and that the other bound is 27. But we did figure out that somewhere in between there, that 18 is the critical point. So we're just going to go ahead and plug in values, some test points as needed. So for instance, for practical reasons, we can just plug in 1, and then we can plug in maybe like 20, okay? So we're just plugging in 1 into the first derivative, and basically that tells me that if I plug in 1, that essentially I'm going to get that it's going to be positive from 0 to 18. But if I plug in like 20, notice that you have 12 times 20 times 18 minus 20, which is actually going to be a positive times a negative, which is actually still negative. Okay, well, what this means is that essentially the function happens to be increasing and then it decreases. That's a little off, but it's okay because essentially I'm done because I've shown that that I have a absolute maximum at 18. Now, in this case, that means that we're almost done because we can actually figure out what the y variable is. So in that case, all that you need to do is substitute the 18 into the equation. So you have 4 times 18 plus y equals to 108. So we have that 4 times 18 is 72. So we're just going to say that y is equal to 108 minus 72, which is 36. So essentially we have that the dimensions of the box are going to be 18 inches by 18 inches. And yeah, it's important that we do include our units. 18 inches by 36 inches. Now, if you want to figure out, like for instance, like what was the largest volume, you simply just multiply by the length times the width times the height. So you just take 18 times 18 and then multiply that by 36, and you're going to find that the largest volume happens to be 11,664 cubic inches. That's because you have that it's volume that's being represented. Okay.